Look at this grid. Dozens of UI avatars smoothly shifting through different geometric shapes, color variants, and status indicators in real time. Modern application design demands this level of visual flexibility. A single avatar component needs to handle dynamic shape masks, online and offline status dots, semantic border rings, and responsive layout scaling, all without breaking the layout grid. In a web environment, building this is straightforward. You hand a list of utility classes, like Tailwind or DaisyUI, over to the browser, and the CSS engine handles the heavy lifting. But this is B4X. We don't have a DOM. To replicate that exact utility class behavior natively, we have to build a translation layer. We need a system that can take declarative styling tokens and convert them into raw mathematical rendering instructions. The B4X DaisyAvatar component serves exactly this purpose. It is a translation engine that intercepts web-style design tokens and turns them into explicit native drawing commands. To understand how this engine works, we have to look at the host environment where it runs, specifically the B4X page avatar implementation. This diagram shows a runtime demo loop. The host page fires off a new variant string and ring width. That data funnels directly into the avatar's internal state machine. Notice the host calculates no pixels. It sends a simple command, and the component handles the rest. If you don't encapsulate this logic, you end up with spaghetti code. You'd have UI pages manually calculating pixel padding, checking screen densities, and redrawing layers every time a user's status changes. A clean architecture enforces a strict boundary. The host page dictates the state. The component entirely manages the rendering pipeline.
Let's follow that data across the boundary into the B4X DaisyAvatar component itself, starting with how it determines its physical size on the screen. A designer passes a standard Tailwind token, like the string SC24, into the setWidth and setHeight methods. The string token enters the Tailwind size to dip function, mapping the web unit to explicit numerical values, 96 device-independent pixels. A native graphics engine requires concrete coordinates. This integer conversion creates a rigid bounding box locked onto a coordinate grid. These computed floats are then cached in the internal state variables mWidth and mHeight, where they wait for the final draw call. Without that parsing step, declarative styling strings have no utility to a native compiler. They must become concrete spatial data first. Once the spatial math is locked down, the component has to actually render the content, and that requires a robust fallback hierarchy. It begins by attempting to load an image path via xui.loadBenApp, but local assets can be missing, and network requests have latency. If the image load fails, Normalize Avatar Type checks for an SVG or text placeholder. If those fail, Resolve Background Color calculates a theme color and draws a solid colored shape to fill the frame. On the web, a broken image link often just collapses the container, ruining the interface alignment. By proactively drawing this fallback state based on the cached dimensions, B4X DaisyAvatar guarantees the parent view's layout remains completely stable. A professional native UI component doesn't assume success. It is built to anticipate failure and execute a seamless visual degradation path. With the fallback system in place, we can look at the most demanding part of the rendering pipeline, calculating shapes and border alignments natively. It starts with the Resolve Effective Mask function. This takes abstract design tokens like the theme's radius box and maps them to explicit rounded corner values, such as rounded XL. But drawing a colored ring and spacing it away from the image with an offset presents a unique math problem when you don't have CSS. A native ring offset is not a box shadow property that just bleeds over the edge. It requires the explicit subtraction of pixels from the canvas boundaries. The insetRectSafe method precisely calculates the inset and contracts the main target area to leave space for a stroke. Then setRingOffset and setRingWidth ensure the inner image and outer colored stroke perfectly nest together without overlapping. Depth layers, triggered by drawShadowLayer, also rely on these exact same manipulated boundaries to position shadows correctly beneath the final shape mask. Emulating web utility styling in a native environment is, at its core, an exercise in strict geometric allocation and boundary management. The final subsystem unifies the avatar's visual presentation through semantic color resolution. A single string token, like primary or success, defines the entire color profile for the component's current state. Here, the state variable MSVariant queries the active palette through the resolveVariantColor method. The token allows the system to retrieve a specific hex code and route it to the placeholder text, the outer ring, and the status dot simultaneously. Functions like resolveOnlineColor and resolveRingColor exclusively pull from this centralized palette. There are no hard-coded colors, ensuring the avatar instantly adapts if the app executes a global theme switch. Separating the intent of a color from its mathematical hex value is the only effective way to scale a UI component across multiple themes. Let's bring this all back to the host demo we saw at the beginning. This fluid, effortless visual output is the direct result of those rigid mathematical pipelines processing in the background. When a user's status changes from offline to online, the execution chain fires instantly. It triggers setAvatarStatus, which calls resolveOnlineColor, which immediately initiates the drawAvatar sequence. Because the component is entirely state-driven and math-backed, that entire sequence completes in fractions of a millisecond, completely avoiding layout threshing. Strip away the internal loops and the layout geometry, and what you are left with is a perfectly encapsulated, predictable visual object. The direct translation of declarative intent into precise, object-oriented state machines provides the performance and predictability necessary for high-end cross-platform interfaces.